we are absolutely living in the age of narrow statistical AI. The leaps we've seen are just, they're
They
astonishing.
really are.
When you think about the highly efficient automation, the large language models, it's changing everything at a breakneck pace.
It is. And the success of this narrow AI, or SAI,
Yeah.
it's concrete. You can measure it. But today, we're sort of looking past that practical
Yeah.
success and into the really deep, often philosophical quest for artificial general intelligence,
AGI.
AGI. And our sources for this, which are just incredible. It's an interdisciplinary editorial with 37 authors. They contrast this huge practical success with the conceptual walls AGI research keeps hitting.
Exactly. So our mission for this deep dive is really to unpack this kind of radical new thinking on AGI, the old model of, just build bigger neural nets, throw more data at them, that's being challenged. Instead, what these experts are arguing is that general intelligence has to be approached through the lens of biology, of
Mhm.
evolution, and they focus on three cross-cutting themes:
Mhm.
agency, autonomy, and autopoiesis.
Which is, simply put, self-organization.
Right.
And to really set the table for this whole conversation, you have to grasp the philosophical shift here. Many leading experts now see human general intelligence not as like an abstract computation problem,
Okay.
but as something that arose from the raw biological necessity of maintaining the homeostasis of life itself, and doing that under inherently difficult, often hostile conditions.
So intelligence is basically a survival mechanism. It's not just a calculator.
Precisely.
Yeah.
And this survival, it demands a really sophisticated suite of features. Things like embodied self-referential information processing,
Okay, so knowing about yourself.
knowing about yourself, the ability for selfhood, empathic mirror systems for social stuff, and critically, the autonomy to set your own goals,
Yeah.
all committed to what they call a hack-free agenda.
That phrase hack-free agenda, that's profound. It immediately takes the conversation away from simple programming and into like security and integrity.
Does.
Okay, so let's unpack this journey. I think Wu et al. Give us a really great framework for it, right? They segment AI's evolution over the last 7 decades into 4 generations.
Yeah, and they frame it using this triad of algorithms, chip technology, and of course, access to data.
So we started AI 1.0, ground zero, they call it.
Right. This was the era of, logic, rules-based inference. Think of your earliest search engines, digital automation. Everything was fully directed by human-programmed logic.
Then things get a lot faster with AI 2.0. This is the deep learning era, the one we're all familiar with.
This is agentic AI, real-time bots, and crucially, the advent of high-performance GPUs in those vast labeled data sets.
And that's what fueled deep learning, reinforcement learning, giving us the breakthroughs in vision and language we see every day.
Exactly. Then AI 3.0, that marks the kind of physical reality check. This is embodiment. It's embedding that digital intelligence into physical things.
Robots, self-driving cars.
Autonomous vehicles, yeah, utilitarian cobots that actually have to operate in, material spaces. The intelligence has to deal with physics.
And that brings us to AI 4.0, the big one. This is the AGI aspiration itself. And this is where it gets really complex, bringing in these, deeply controversial ideas like machine sentience.
And the ability for machines to engage in the autonomous selection of goals.
Right, and that's the flashpoint, isn't it? The autonomous selection of goals.
That's exactly where the engineering and philosophical conflict flares up. It introduces the core problem of alignment.
The alignment problem. The risk that an agent that can set its own goals might not align them with, human values.
That's safety.
Or survival.
Right. But Marcos gives this crucial counterpoint. He argues this isn't a unique AI problem. It's foundational to civil society, even to biology.
How so?
Well, in biology, conflicting adversarial goals.
Yeah.
They have to be constantly identified and rejected for the species or the code to survive. The key insight from the sources is that we should be looking for alignment lessons in the evolution of life itself.
This is where the idea gets really wild. The genomic intelligence hypothesis. The editorial is suggesting that life already solved alignment and selfhood, and it did it in formal code-based ways. And to explain it, they use concepts from Gödel logic and, unbelievably, blockchain technology.
It is truly mind-bending. The core view is that life established its sense of self through these code-based integrity systems. Marcos conjectures that about 85% of an organism's express genes.
The genes that dictate how it looks, its phenotype.
Exactly. Those genes can be viewed as its foundational theorems. This is the established known code of the self.
Okay, so the body itself is the established theorem, but if that theorem is always under attack, what's the defensive algorithm?
That role is played by the adaptive immune system, the AIS. It evolved in jawed fish about 500 million years ago. That and our mirror neuron systems. These things function as an offline thymic self.
A self-representation structure, like a constant internal security audit.
That's a perfect way to put it. So the thymic self isn't the gland. It's the system that decides what is self versus non-self.
Okay.
And its entire job is to recursively identify what they call non-self codes. These are the digital adversaries, like viruses, that wield the negation operator.
They're trying to corrupt the self codes.
They're trying to negate them. And the problem is existential because the number of potential adversaries is, well, it's an uncountable infinity.
So the immune system is basically running a continuous security check against an infinite number of possible cyber attacks. This is where the digital analogy gets really specific, right? The Gödel logic connection.
This is the boldest part of the hypothesis. The Gödel sentence, that famous statement that's true but you can't prove it within its own system, is conjectured to act as a hashing algorithm.
Wow. Like in a blockchain?
Exactly like in a blockchain. It allows this embodied self-referential intelligence to quickly detect any negation or misalignment of its own self-codes. It maintains the integrity, the unbroken chain of life's digital ledger.
That is. Wow. So the body has a built-in auditor that uses pure logic to verify its own digital signature. But is there any discussion about how an engineer would actually code a Gödel sentence into an AI?
That's the multi-million-dollar question, isn't it? The sources don't give you a blueprint for coding it. They frame it as a necessary condition.
I see.
They're saying any true AGI must have some kind of meta-level function that's perpetually verifying its own integrity against negation, just like our immune system does.
And that necessity, that need to detect negation, it just naturally leads to conflict. I know Binmore first identified this back in '87 with Gödel's liar paradox. It implies a perpetual arms race.
It has to. This self-regulation is always accompanied by an arms race in novelty or, surprises. It's a constant battle to maintain the primacy of the life codes against the adversary. Intelligence is inherently combative.
It really forces you to see that survival and self-preservation are maybe the highest forms of intelligence, and that self-regulation has to translate into dynamic processes, which is where Richard will come in, right? Moving beyond simple homeostasis.
Yes, moving to allostasis.
Allostasis. Okay, so homeostasis is static, keeping your temperature at 98.6. What's the fundamental difference?
Allostasis is all about anticipation, prediction. It's dynamically monitoring and controlling a ton of different parameters to maintain the stability of the integrated self, not just its individual parts.
Give me an example.
Okay, if you know you're about to run a marathon, your body doesn't wait for your temperature to spike. It raises your heart rate and blood flow in advance. It's adaptive, predictive control for the whole system.
And they actually tested this.
They did on an allocentric synthetic agent in a virtual world. The agent had internal needs, like heat and hydration, and it faced stressors. The model with allostatic regulation successfully maintained a robust balance, stabilizing the whole system even when the environment was actively trying to mess with its goals.
So that's the internal self. Let's shift to the external. How does this dynamic selfhood play out in social interaction? Koch et al. Looked at this.
Yeah, and they emphasized that human social cognition absolutely requires individual autonomy.
Which makes sense.
It's non-negotiable for social intelligence, because social cognition relies on deep self-knowledge, both internal, your interoceptive awareness, and external, from your sensory motor cortex. That integrated self-knowledge is the foundation for empathy.
For predicting what others will do. If I know how my body reacts to something, I can guess how yours will.
Exactly. And that's why any remote-controlled robot, or an externally programmed one, can't qualify for true social cognition.
They're just puppets.
Correct. Even swarm robots that self-organize along limited, externally defined rules, they lack the necessary autonomy. They can't truly engage socially because they lack that core of self-reference.
And just like the genomic self has to deal with the viral adversary, the social agent has to face the social adversary.
Exactly. They connect it right back to Binmore's work. They stress that autonomous social robots, just like us, have to be able to detect liars or adversaries agents doing unpredictable adversarial things, and be ready to enter into an arms race with them to protect their own autonomy.
Social intelligence requires a built-in deception detector.
It has to.
This constant pivot back to biological necessity, to defense systems, it does raise a central question for engineers. Do we have to start building AGI from a human-level blueprint? Pontus Fido and their team challenge that.
They do, with their concept of neuroevolutionary AGI, or NAGI.
So what's the approach?
NAGI suggests a more low-level evolutionary path. Instead of trying to code human-level complexity from the top down, you start at a much more fundamental level, with a body and a reactive environment, and you let complexification happen naturally.
So how do they do it? They use a randomly initialized spiking neural network.
Yep, and learning happens through adaptive synapses and a reconfigurable network topology. The method's called neuroevolution of augmented topologies, or NEAT. And the big deal here is that it avoids gradient descent.
Which is what traditional deep learning relies on. Why is avoiding it so important?
Because gradient descent requires massive computational power and just enormous data sets. By using evolutionary strategies like NEAT, which adapt the network structure over time based on performance, they avoid that data-hungry brute force approach. It's a more frugal path to complexity.
And it worked.
It was successful on tasks like food foraging, emulating logic gates, and the classic cart-pole balancing problem.
Fascinating. So that's one alternative. Another comes from Johansen and Chen, focusing on learning by doing and machine psychology.
Right. Instead of evolution, they're looking at behavioral science.
Yeah.
Johansen combines operant learning psychology, the whole stimulus-response-reward triad, with the non-axiomatic reasoning system, or NARS.
But they add something to the triad, right? The establishing operation.
The establishing operation, or EO. And it's crucial. It's the context that changes the value of the reward. For instance, being hungry is the EO that makes food a highly valuable reward. It gives the model motivational context.
I see. And NARS is good because it works with limited knowledge.
It's highly effective under conditions of limited knowledge and resources. It doesn't need to be trained on the entire internet to make useful inferences.
So it's efficient, which connects directly to the Chen et al. Paper on fast and frugal heuristics, bounded rationality.
Absolutely. We don't optimize every single decision we make. We satisfy.
Yeah.
We pick the good enough option quickly. Chen and their team literally watched people solving simulated treasure hunts under stress.
With like fog and time pressure.
To figure out what these simple, effective decision rules were.
And when they put those simple, good enough rules into autonomous robots, what happened?
The robots showed significantly better robustness and adaptive behavior than robots running on complex optimization algorithms, especially when faced with unexpected problems. It proves that sometimes the simple fast rule is just more resilient in the messy real world.
So Johansen's second paper builds on that, trying to capture our most flexible learning facility, arbitrarily applicable relational responding, AARR.
AIR is our incredibly flexible contextual learning. It's the ability to apply a relationship learned in one context, like A is bigger than B, to a totally new and unrelated context, like C is more abstract than D.
And he showed that this could emerge from NARS.
He did. He combined NARS with behavioral psychology and showed how key AIR properties can emerge directly from NARS's inference rules. It suggests that complex, flexible, human-like intelligence might be achievable through constrained, elegant systems, not just massive data processing.
Okay, so moving back from the theoretical to the practical, let's touch on how current statistical AI is being refined. Zhai et al. Looked at the complexity of multimodal intelligence in robots' vision, audio, language, all at once.
Right, and they focus on what's called multimodal, named entity recognition, or MNER. It's vital for processing noisy, real-world data, like, say, social media posts with short text and an image.
Yeah.
And their enhanced architecture for feature extraction worked well, but the improved performance came at the cost of being significantly slower. It's that classic trade-off. More accuracy often costs you time.
Meanwhile, Babushkin and their team were trying to overcome human bias in assessment using a TCN, a temporal convolutional neural network, to evaluate handwriting legibility.
And the key finding there really reinforces that whole embodiment argument we've been talking about. The TCN did okay using just the stylus kinematics, so just the output of the pen.
Okay.
But its accuracy jumped by about 10% when they added hand kinematics features.
So you have to teach the machine to look at the human body, how the hand actually moves, the tremors, not just the final pen stroke. That's a really subtle but powerful insight.
Exactly. You lose so much valuable data when you only measure the endpoint.
And finally, a great example from medicine. Binzager and Abulfaraj tackled overfitting in CNNs used for diagnosing Alzheimer's from MRI scans, a notoriously noisy dataset.
Overfitting is just when the model learns the noise instead of the signal. Their solution, the NGSA framework, It combined a generalized self-attention score to filter out irrelevant details with an extreme learning machine classifier.
And this combination did what, exactly?
It achieved superior diagnostic performance by basically teaching the AI what not to look at.
Ah.
It improved its global awareness before it made a localized classification.
This has been a really comprehensive exploration to kind of bring it all back together. The search for AGI is pivoting, and it's pivoting dramatically. What are those three inescapable themes that are emerging?
The research is just consistently pushing for agency, autonomy, and autopoiesis self-organization as necessary foundational features. They're moving away from intelligence as a passive calculator. In fact, they even coined a new term, codiopoiesis,
Codiopoiesis.
to specifically describe how this code-based genomic intelligence achieves self-organization in a way that mirrors robust, decentralized processes like blockchains.
The ultimate takeaway for me, then, is that the journey to AGI it's looking more and more like a mirror held up to life itself. We're being forced to understand the mechanics of our own immune systems, our genomic structure, our self-regulation, just as much as we're focused on new silicon architectures.
It forces us to appreciate that intelligence, at its core, is about integrity, defense, and self-preservation above all else.
Which leaves us with a provocative thought for you to chew on. If complex life by evolutionary necessity is configured to be an active participant in a perpetual Gödelian arms race to defend its own self-codes, that constant, necessary conflict to detect and negate the adversary, what ethical and safety implications does this pose for developing fully autonomous, self-improving AI systems? Can true AGI even exist without the evolutionary necessity of perpetual conflict?